All right, so the Chapter 5 Getting Started activity, we did this a couple days ago, and you had your test on Chapter 4 yesterday. And so what we want to do is we want to talk about, I'll briefly recap the activity and what you guys did and what all these numbers mean, okay? So we started this chart and asked you to finish this chart by putting the averages. I don't know if you all did averages or if you just added them up and changed this number. But the game was roll 2 dice and calculate the difference between the numbers on the dice. And so in this first chart, this represents our experiment. Okay, so this is going to be the experiment numbers right here for our actual trials. And this each row were submissions from each of 2 groups. So we had 1, 2, 3, 4, 5. We had 10 groups. You combined your numbers, and that's what we got. So the difference of 0, so that's when you rolled the dice and each of the numbers were exactly the same, had a difference of 0. And so the average out of, and we calculated this out of 72, we did 36 trials and you combined your numbers. So it's an average of 12.4 times out of 72. That the difference was 0. The difference was 1, so if you had a 2 and a 1, or a 3 and a 2, or a 4 and a 3, or a 5 and a 4, or a 6 and a 5, the difference being 1 happened 21 times out of 72, and so on. And so these are the numbers, and these red numbers down here are the averages for the trials. Okay? Now, I know if you add these up, I did this several times here. I think somebody gave me a wrong number because all of these averages only add up to 71.6. So I think somebody maybe from the numbers that we've got here, one of these numbers might be wrong. However, it's going to be close enough anyways. So that's the experiment, and down here in this chart I asked you to write down the experimental probability. And so these were my calculations. You can double check with yours to make sure that those are correct. But I basically took each of these numbers here and divided by 72 and wrote them as a decimal. So probability can be expressed as a decimal between 0 and 1. 0 means there's 0 chance of this happening, or 0 probability this will happen. And 1, exactly 1, is an absolute certainty that it will happen. Okay? So anything in between tells you sort of what the likelihood of an event happening would be as in terms of probability. So we can write this as a decimal, which I have in this chart. You can also write it as a percent, right? If you think about the weather, you hear on the weather there's a 17% chance of probability, 17% chance of precipitation. Okay, so that would be 17 times out of 100. When we've seen these same conditions before, it's rained, and so they're saying based on experimental probability, there's a 17% chance that it'll rain. So that's where you've heard that before. You could also write as a fraction, so 12.4 out of 72 or whatever, that sort of thing. You don't want decimals in fractions, but you get the point. And it also could be a ratio too, like 12.4 and then dot dot, right? Like you could also write a probability like this, kind of as a ratio like that. All right, so you've learned all that stuff in math classes before. We'll just stick with probably decimals and maybe percents here. So everyone understand the experimental probability is based on actual experiment that you guys did, and these were the numbers. So there's the largest chance is a 1 difference, okay, a difference of 1. That's here. That's 0.29. All right, the next one was a difference of 2, and a difference of 5 happens the least amount of times. Okay? If you think about that, that should make sense. And the reason why this should make sense is because what you do without even knowing it is you're thinking about, well, what logically would I expect? And that's what theoretical probability is. Okay, I'm not sure why I messed up so bad on that letter. Theoretical. Okay? Probability. So you're thinking, now I don't know if you thought this or not, but look at here number 1, right? The difference of 1. Well, if you think about the dice, okay, 2 and 1, 3 and 2, 4 and 3, 5 and 4, 6 and 5, those are all opportunities where you could get a difference of 1. Where you get a difference of 5 only happens when you have a 6 and a 1, right? So that doesn't happen very often. So right here, that is when you have a 6 on one and a 1 on the other. or if you have a 6 on one and a 1 on the other. So, logically, it's tougher to get a difference of 5. Easy to get a difference of 1. And that is reflected in our probability. So theoretical probability, what we want to do is you want to basically take a look at a chart. And this would be an outcome chart or outcome table. And of course, these are the numbers on the dice here, right? This is dice number 1, dice number 2, whatever. And you could roll a 1 and a 1. And that difference is 0, and you put the difference in there. So we started this last class. But this is a theoretical probability outcome table, right? And so if we count the number of zeros in the table, 1, 2, 3, 4, 5, 6. So there are 6 opportunities out of the total 36 possible outcomes. 6 out of 36, which roughly is 0.17. So on your calculators, this is what we're going to do. We're going to run through these numbers here, and we're going to compare them with our experimental. So just once again, 1 divided by 6, or I guess, there's 6 divided by 36. That's where that number comes from. And 0.16667. So I'm going to maybe change that because I used more decimal places than the other one. Okay. All right, so you completed your chart here. So what did you get for 1? How many chances of 1? What's the probability? Go ahead and shout it out. Okay, agreed. 0.28. Is there more decimal places? Is that rounded? Okay. What did else you guys get? What's more decimal places? Anybody write down more decimal places there? Okay, 0.27 repeating. Okay, 28 is fine, but I'll keep with the more decimal places here. So I'll just extend that a bit. Okay, and number 2, go ahead and shout it out. What is number 2? 1, 2, 3, 4, 5, 6, 7, 8. That's 8 out of 36. What's that as a decimal? .2222. Okay. Did everyone finish this chart, or you guys know what you're doing? Okay. So what about number 3? How many 3s are there? 1, 2, 3, 4, 5, 6. So that's 6 out of 36. That must be the same as this one, I guess, right? So 0.1667. Okay. And what about 4? What'd you get for 4? Thank you. 1111. Right, that would be 4 out of 36 or 1 out of 9. And 5. Thank you. 0.055, rounded to 6. All right. Okay, so now the important thing here is the theoretical is what you would expect, right, based on the nature of the situation. This is what we would expect. Theoretically, and you've heard people talk, right? Well, theoretically, this is what should happen, or theoretically, this is the way it's supposed to be, right? In theory, that's what it means, in theory. So if we're rolling 2 dice, if we're talking about the difference between the numbers, theoretically, this should be the probability right here. Theoretically. Theoretical probability. Yes? Got it? Experimental probability is just that. It's based on experiment. Now, if we did one experiment, or even if I took one of these trials, okay, do you see how these numbers here, 15, 27, 9, 10, 8, 3, very different than the average, right? Very, very different. So if I just took 15 out of 72 and put my number down here, and 27 out of 72 with one trial, then these numbers would be drastically different. The more trials we have, and here we've taken 10 groups and we've averaged, okay? We've averaged the numbers of 10 groups, and look at how our numbers are actually pretty close, right? 0.17, 0.16, almost exactly 17, right? 0.29, 0.27, 0.20, 0.22, and so on. So these are actually pretty close. And you will find that as you get more and more, as you do more and more experiments, or you gather more and more data, the experimental probability will start to come closer to the theoretical. Right? Another example, if you flip a coin, right? There's a picture of the queen here. Okay, there's the queen. Okay, not sure what she's got around her neck there, but anyways, it's some kind of, there's the writing, and Regina, of course, is on here too. Yes. Okay, or Fair City. Anyways, you flip a coin, you could have heads, right? Or you could have what? Tails. Okay, so depending on what we have here, you could have, I don't know, what are we going to do? What's this? What's this coin? Yeah, it's a dime. That's supposed to be the vote. Okay, so that's tails. All right, here's the year. Da-da-da. Okay, looks like I messed up face a little bit. So heads and tails. Now, if you flip a coin, the chances of getting heads are what? Sorry? 50%. 50-50. Okay? 1 to 2. 1 out of 2. There's two options. There's two options. And supposedly, each one of these options are, this is very important, listen up, are equally likely to occur. There's no favoritism here, right? This is what we're assuming when we flip a coin. It's 50-50, right? If you shoot a free throw in basketball, hopefully, all you basketball players, hopefully, there's only two options, right? Hit the basket or miss the basket. But hopefully, your chances are not 50-50. Hopefully, they're better than that, right? Because you practice and all that. Now, if you're Shaq, it's way less than that of getting it, right? What was he, like 17% in the free throw line or something? Most of his career. It's terrible. Anyways, he probably could have dunked it from the free throw line, but anyways. You see what I'm saying? There's not an equally likely chance that you'll get a basket if you put in the time in practice, because you'll make more of them, probably, right? But flipping a coin, equally likely. So what we're going to be doing today is we're going to be talking about 5.1, and we're talking about fair games. We're talking about games, talking about likelihood, probability of all outcomes being equally likely to occur. So, lucky for you, I don't know, maybe it's lucky for you, I'm not sure, but we're going to be playing a game in class here today. And so I'm going to get you set up with that game, and I'll just kind of throw the textbook on the screen here so you can see what you're doing. Okay, so here's the game. It's 5.1, we're exploring probability, and we are exploring the concept of a fair game. As I just mentioned, a fair game is a game in which all players are equally likely to win. Okay, equally likely. There's that phrase there. For example, tossing a coin to get heads or tails is a fair game because there's no bias there. It should be just 1 out of 2. There's no way that one person should be able to win every time, right? That's a fair game. Now, this game is a little bit more complicated than just heads or tails. So you have to think carefully. And I want you to, I'm going to give you a good amount of time here this class to go through this, to play the game, to think about the game, and to figure out whether it's fair and why or why not. Now, what you do is this. 2 people, okay, you each have 3 slips of paper. On those slips of paper, write the numbers 1, 2, and 3. Now, you can fold them or whatever. What you're going to have to do is randomly draw, okay? Randomly draw a number each time, so it's not the same one or whatever, it's just random. And for each turn, both players draw 1 slip of paper from their container or from wherever. So, you have to figure out who's player 1. So player 1 is the product player, and 1 player is the sum player. So player 1 scores a point if the product of the 2 numbers is less than the sum. Okay? Player 2 scores a point if the product of the 2 numbers is greater than the sum. So it looks like player 2 might be the product player. So if the product is greater, then player 2 gets a point. If the sum is greater, player 1 gets a point. Get it? Does everyone understand? Any questions? Okay, shouldn't be that hard. Just think about it, read through it. After each turn, the players return the slips of paper to the container. A game consists of 10 turns. Okay, so this is Sasha's game here. Okay, Micah and Sasha are playing. So is Sasha's game fair? Once you do this game, consists of 10 turns. Okay, record your points, and then you can congratulate the winner. Of course, it's going to be pretty huge here. Then you answer these questions. Talk about it amongst your group. Okay. And also, if you want to think about the theoretical probability here, okay, there's a way that you can determine whether this is fair or not, thinking about a theoretical, from a theoretical point of view, just like we did over here. Here's the experimental side. Here's the theoretical side. So see if you can think about how you could prove whether this game is fair theoretically or not as well. Okay? So take some time, play the game, think about it, write down your observations, answer those questions from the text. And I'll leave these questions up on the board in the instructions. So Sasha's game that you all just played consisted of 2 piles of cards, and we had little slips of paper with the numbers 1 to 3 written on them. Each player randomly picks a number from their pile, and you show each other the numbers, and if the product of the 2 numbers is greater than the sum, then whichever person is the product person, and you decide this ahead of time, gets a point. If the product is less than the sum person gets the point, and if the product and the sum are the same, then no points are awarded. So just out of example here, this person picked a 2, this person picked a 3. If this person over here is the product person and this person is the sum person, who gets a point? Which one? The product person gets a point. Okay, well 2 times 3 is 6, and 2 plus 3 is 5. So yes, the product, this person gets a point. Everybody see that? So this is the game that you just played. You did this 10 times, and I want to know from each group now who won the game, the product person or the sum person. So let's just make a chart here. So product and sum, because remember, it's experimental probability, so we might not all get the same answers, but let's just see overall what the general trend is here. Okay, so group 1, or you guys didn't actually play it properly, did you? Okay, group 2. Sum 1, okay, you guys? Some person 1? Some person 1? Somebody 1? What about you guys? Product 1? Okay. Some person 1? Okay. Some? Which one who won your game? You tied? Okay. Tied. Okay, so there's 1 for that category. The product person or the sum person? Which one? Well, whichever you guys were playing, did you pick, like, was player 1 the sum person? Okay, so you got a sum. Sum. And anybody else? Or no? Is that all the groups? Okay. So it looks like if you were the person that picked the sum, if you were the sum player, then looks like obviously you won more often than not. So based on experimental probability then, from what we see up on the board here, is this a fair game? Does it appear to be a fair game? No, it doesn't appear to be a fair game if the sum person wins this many more times than the product person, right? Okay, so some person has the advantage. What about theoretical probability? As I was walking around, I saw I saw one, some, S-O-M-E. I saw one group that had a good theoretical probability explanation. I only saw one. So does anyone, now you guys just hang on, I want to hear from you in a second. But did anybody else have a good proof for, did you end up proving that the sum person would have a theoretical advantage? Yes, you guys did? Okay, can you explain to us real briefly kind of what you did? How did you determine that? Okay. Okay, so you made a table with the 1, 2, 3 here, and the 1, 2, 3, and you made a product outcome table and a sum outcome table. That's what we're saying? Perfect. Okay, and so that's great. That's awesome. So then there's a sum one down here, and you found out what? That the sum person wins more. Okay. So if we look at these two tables, what you have to understand is that this and this are the same turn, right? This is one turn. If a 1 and a 1 shows up, then who wins? The sum person wins here, okay? What about for this next one here? If a 2 and a 1 show up, who wins? Yeah, sum person, okay? And this one here, obviously sum would win again here. Going down here, 3 greater than 2. So yeah, so the sum person is winning all of these turns so far. What about this one? Yeah, it's a tie, so nobody wins that. What about over here? Oh, we've got a product winner, right? Over here, got a sum winner, got a product winner, got a product winner. So if you did this, you would find that there are, out of the 9 chances, out of the 9 possible opportunities, the sum person should win 5 times out of the 9, and the product person should win 3 times out of the 9, and nobody would win 1 time out of the 9. Okay? So that's good. The other group that I said I would come back to, you guys did the same sort of thing, right? You did 2 and 1, and then you said who would win this, right? Well, the sum person would win this, 2 and 2, and so on. You listed all the possibilities, and you wrote down sum, product, nobody here, right? Product, and you did all that, and you counted them up, right? That's perfect. Anybody else prove this theoretically a different way? Anybody think about this a different way? Okay. What about the other questions then? Okay. So that's a one. Okay. I guess I don't see the question here. Where is it? It's somewhere. Oh yeah, it's the first question on the assignment. So it says, how would you make Sasha's game fair? Did anyone have any idea? I know you probably haven't thought about this. It wasn't a question I asked you to think about during the activity, but any of you have any ideas of how we could make this game fair? How we could change it to make it fair? Make one other number a tie? Okay. So if we go back to our chart here, so like one of these, you're saying one of these spaces, if we made one of these other options a tie, then, so like if I took this one out, made that a tie as well? Is that what you're saying? Okay. Well, you still have 4 opportunities here for the sum person to win. So you'd have to do 2 of them, okay. Okay, so maybe if you change this and you do doubles, any doubles would be a tie. So this one would be a tie, this one would be a tie, and this one would be a tie. So then nobody gets that. 1, 2, 3, 4, and then, yeah, and so then that would take this one out too. So, okay, this is good thinking though. I like that. I like that thinking. That's going to be part of your assignment, is to think how you can make this fair without just looking at the back and writing that answer down. I want you to try and think about it. See if you can change the number of numbers, that sort of thing. So think outside the box, literally here a bit. Okay, what else do we need to talk about here? Okay, let's go back to the book and let's just formalize what we've learned, okay? The big thing I want you to take away from this lesson today and from yesterday as well is the difference between experimental probability and theoretical probability, okay? In this last example, the theoretical and the experimental, they matched up, right? The sum person won more than the product person. Although, the sum person won far more times than they really should have, right? It shouldn't have been this lopsided, according to our probability, right? 3 out of 9 versus 5 out of 9. Okay, that's different than this. What is this? This was 7 out of 8, right? Or 7 out of 9 and 1 out of 9, right? So that's not quite the same, but we got the right winner. So experimental probability. Let me just talk a little bit about this notation. Okay, knowing the probability of an event is useful when making decisions. Experimental probability, of course, is based on previous experience, right, or a previous experiment. And that is given by the probability of event A. So an event is just something that's likely to happen, something under consideration here. And the probability of event A in theoretical or in experimental is the number of times that A happens divided by the number of times that T would happen, and that's the total number of trials. So A, the number of times A shows up divided by the number of times, the total number of trials in the experiment. So that's a little bit different than theoretical probability. Theoretical probability states that the probability of event A is the number of times that A, and they're also referred to as favorable outcomes, Okay, so when A happens, if A is the event under consideration, if A actually shows up or it actually happens, that's called a favorable outcome. So this is the number of times that A happens, event A happens, and S, okay, is the total number of outcomes in the sample space. So that's where we draw those tables and we say, all right, what are all the possible outcomes? Whether we actually would get any of those in an experiment or not, right? That's the difference. What are the possible chances that we could possibly have? So that's the difference there, the sample space. So T is the number of trials that we do, okay, and the number of times that something else shows up or whatever, the total number of things that show up, the number of trials, and S is the sample space. So, and that sample space is considered where each outcome in the sample space is equally likely. So it's maybe a bit of jargon, for you, but it's probably good to have the actual definitions and formulas there to just kind of ingest those a little bit, so you kind of get to know the wording and some of the terms. And of course, a game is fair when all players are equally likely to win. All right. All right. So here's some other information as well. I'll get you to look at here, and I'll give you your assignment in a second. All right. So for 5.1, okay, I'll get you to do those questions there. It's just 4 questions. So 5.1, do number 1 to 4. That's on page 303. So again, just some more, just some exercise there on fair games and probability. Any questions?